Okay, lesson 49 is concavity and inflection points, geometric mean of the second derivative, and first and second derivative test. We have worked with first and second derivatives. We have worked more with first derivatives because I know there have been multiple times that I've started to talk about the graph's concavity and I realized, oh, we haven't really talked about concave up versus concave down, and so today we get to talk about that. So when we talk about the concavity of a graph, you'll notice it's defined as the bowling of a graph, as you guys already talked about bowling. So the bowling of the graph, which way does the graph curve? Okay, is the curve curved so that the shaping is up, so that you could set something in it, or is it curved so that the shaping is down? Okay, so concave up versus concave down. When we talk concave up, okay, if concave up, the graph will be bowled upwards. So any part of a curve that is concave up has that upward shape. If something is concave down, the graph will be bowled downwards. And not your bowling ball bowled, but like the shape of a bowl.
We should call it
a bowl you eat your cereal out of.
bowling versus
Okay, now, when the concavity changes, so when your graph, as you're tracing your graph and it goes from concave up to concave down or vice versa, that's what we call an inflection point. Okay, an inflection point falls into that category of critical points. So it falls into the category of your mins and maxes and inflection points. So, for instance, you have like a cubic looking graph here. As you think about a cubic graph, the whole graph itself is increasing because the whole graph is moving up as you move from left to right. But the beginning of the graph, kind of like up until 0, 0, the curve of it is concave down because the shape is bowled down, so to speak. Okay. Then when you hit that 0, 0, that's what's called an inflection point because now all of a sudden my graph changes and now it's bowled upwards. Okay. It's kind of like the first part you have part of an upside down parabola. Well, that's concave down. The second part you have part of a right side up parabola and that's concave up. Okay. I know there's conversation earlier about PIP, possible inflection point. Okay. And inflection points, I talked about inflection points being critical points like mins and maxes, right? Inflection points are going to happen when the second derivative equals 0. So when that second derivative equals 0, it can be a min, a max, or an inflection point. Okay, so let's look at example 1. Shown below is the graph of f. Indicate if the graph appears to be concave upward, concave downward, or to have an inflection point at the points labeled. So basically we're going to look at each section here, so to speak, and decide is what is happening.
Why are they both called concave instead of one being concave and one being convex?
I don't know why they don't. You don't hear convex in calculus. They just do concave up and concave down.
That was kind of confusing to me as well. I figured it was someone else.
I can't think of convex being in calculus. I really can't. So remind me, it's been a few. Because when you guys talk about concave and convex, you talk about like mirrors and stuff? Or what do you guys use it in terms of?
It's like irregularities, like sometimes on surfaces, there'll be like concave surface or convex surface.
Okay. So what's the difference between concave and convex then?
Convex goes in, but concave goes in, but convex comes out.
Comes out? Yeah, I don't know. I mean, I don't have a good answer of why it's concave up and concave down versus, I'm trying to think. I don't know, I have to think about that. Because I'm trying to think on the spot, and I don't know. I have some thoughts forming. but I have to think through it more thoroughly before I express those thoughts. So, yeah, I honestly don't know. Okay, so as we look at each of these points, okay, point A, and actually we're going to go through all of these points, A, B, C, D, E, and F. What do you think is happening at point A? Is the graph concave up, concave down, or is it an inflection point in between? Okay. Is this part of a bold downward grouping? And yes, A is what I would call concave down. I'm going to use CD for that. Does that work? CU for concave upward, CD for concave down, and IP for inflection point. Okay, so A is concave down. That curve is facing opening downward. Okay, what about B? Still opening downward, isn't it? Okay, the idea of like a whole parabola. If it's just a parabola, an entire parabola is either concave up or concave down. And so like this first parabola here is concave down. So A and B are both concave down. What about C? Okay, you see C being an inflection point? So we've got this parabola above it that's concave down. And then at C, that's approximately the point that now we're going to change what we're doing. So C is an inflection point. What about D then? Okay, that's a parabola opening upward. And so that is concave up. Okay, E. Okay, again, we're changing from our parabola opening up to something opening down. And so E is going to be another inflection point. What about F? Concave down. You feel okay about that? The difference between concave up, concave down, and where those inflection points happen? Okay. Well, let's continue along then. Part B, we start talking about the geometric meaning of the second derivative, so just all that goes along with concavity here. So determining concavity and inflection points is similar to what we did to find our max-min values. We simply use the second derivative instead of the first derivative. So notice what it says here. If the second derivative is positive, so specifically second derivative is positive when x equals c, so x equals some point. So any place the second derivative is positive, the slope of the graph of the function is increasing as the x-coordinate increases. Thus, the graph is concave upward. Okay, so it's short of that. When the second derivative is positive, your graph is concave upward. Okay, so what's that mean when the second derivative is negative? Yeah, when your second derivative is negative at a certain point, then notice it says the slope of the graph of the function is decreasing as the x-coordinate increases, and thus the graph is concave down. And do notice here, when they talk about the slope of the graph of the function, they're talking about the first derivative, right? So they're talking about the slope of the graph that is decreasing. So they're saying the graph is decreasing as the x-coordinate increases. Okay? So I was kind of debating if there's more I wanted to explain there or just kind of go with it. I think it'd be easier just go with it as we move into these examples and explain there. Okay, before we go into example 2 right here, note, I just kind of mentioned this, the first derivative. Remember, the first derivative tells us the slope at a certain point. Okay? Now, example 2. Looking at this graph, at which of the points labeled on the graph shown is the second derivative positive? So, this is essentially the graph of f. They want to know when is the second derivative positive. So they want to know when is f prime, f double prime, greater than 0. So if this was the original graph of f, and we want to know when the second derivative is positive, what would I be looking for there? Not necessarily just that. When is the second derivative positive? When the graph is what? Concave up. So if they want to know when is this, if this is a graph of f, and they want to know when is the second derivative positive, they want to know when is this graph concave up. When is this graph concave up?
Between but not including points B and D.
Partially agree.
Actually not, it'll be just hanging after.
Okay. So, what would you guys say about C? C is definitely, my graph is concave up there, yes? Okay, so we can definitely say C. Now, Daryl, you mentioned something up to but not including B. So what is B? Right. B is an inflection point. So at that, and really the question is just at which of the points labeled. So at B, is my second derivative positive? No, my second derivative would be 0. Okay. C, my second derivative would be positive because it's concave up. What about D? Yeah. Based on the way this graph is, there's nothing that says this graph ever turns and goes back down, does it? So we're going to assume that this keeps going up. And so if this keeps going up, then D is also concave up, and thus my second derivative is positive. What's going on at point A? Point A is concave down, and thus my second derivative would be negative. Okay? So, first derivative tells us whether the graph is increasing or decreasing. Second derivative tells us if the graph is concave up or concave down. And that leads us into how we can use the first and second derivative test. It is a lot of words. Now, I talked somewhat about we didn't refer to it as a first derivative test, but I've essentially talked about the first derivative test when we've done other things. We talked about it not too long ago when we were trying to prove, I'm trying to remember what it was on. It might have been on a review worksheet or whatever, but we were trying to prove that something was a min or a max. And I said, okay, to show me something is a min or a max, you can't just say, oh, the derivative equals 0 at this point, so it has to be it's a min or it's a max. To prove it, you have to look at what's going on either side. And we had to look if the first derivative was increasing or decreasing. That's essentially what this is saying. So notice, I'll dissect this for you guys. Suppose f prime of c equals 0. So this is saying suppose the first derivative at some point equals 0. So that's saying that point, what do we usually say, is a min or a max is our general, what we say, right? Okay, so if the derivative of f, so the slope of the graph of f, is positive for all values to the left of c and negative for all values of x just to the right of c, then f of c is a local maximum. Okay, let's break that down. If the derivative is positive for all values left of C. Okay, so think about, here's my visual for you. Here's C. If the derivative is positive to the left of C, what's that mean is happening to the graph left of C? It's increasing, yes? So to the left of C it is increasing. And then it says, and negative for all values just to the right of C. So if my derivative is negative to the right of C, what's that mean? It's going down. It's decreasing. What did we just make C into then? It is a local maximum. So the idea is if your first derivative is positive on the left, right, and increasing graph. Or excuse me, a maximum on that graph. Okay? 2 is just the opposite. I'll put my visual of C over there. If the derivative of f is negative for all values to the left of C. So what's that mean if my graph is negative? If the first derivative is negative, it is what? It's going down. It's decreasing, right? So if we're decreasing to the left of C, and then if it's positive for all values to the right of C, whoops. If my first derivative is positive, what's it doing? Increasing. So if we decrease to a point and then increase away from the point, what is that? It's a minimum. Okay, so this is officially your first derivative test. You have to do this to prove something is a min or a max. Now, okay, this is the part we haven't talked about before. Point 3. If the derivative has the same sign for all values of x, just to the left and just to the right, then C is an inflection point. So think about that. If my derivative is negative in both places, that means that I am decreasing, right? If it decreases left, decreases right, but you have a critical point, a critical value there, then it's not a min, it's not a max, it is an inflection point. Same thing if it's increasing. A good example of this, what graph have we already drawn that would have this happen? The cubic graph is the one I talked about today. That because the cubic graph is just y equals x cubed is always going up. So even though there's that curve in the middle, then it's going to be an inflection point. Okay? It can't be a min, it can't be a max if it's increasing or decreasing on both sides of a point. Okay? And let's see, I'm trying to remember what so just kind of a side chart here. Remember, if the derivative equals 0, critical number. If the derivative is greater than 0, increasing. If the derivative is less than 0, decreasing. Okay, that's your first derivative test. As I said, we talked about that the other day. I can't remember what that was on, but I know we talked about it. So let's talk about second derivative test. So now, suppose that which one is this? Okay, it is supposed to say that. Sorry. Okay, so suppose f prime of c equals 0. So notice this is supposing the first derivative equals 0. That defines it as a critical point for us, right? So min, max, or possible inflection point. Now, notice what it says. If the second derivative is a negative number, so if it's at a critical point, okay, sorry. First derivative equals 0. The second derivative of f is a negative number at x equals c. Then f of c is a local maximum value. Think about this. If the first derivative equals 0, that means most likely a min or a max, yes? Well, if the second derivative is negative, second derivative negative means concave what? Second derivative negative is concave down. Yes? What happens when a graph is concave down? Does it make sense that there's a max there? So local maximum value. Okay? So, again, goes back to first derivative equaling 0, so critical point, min or max. Second derivative can tell you which it is by looking at the fact that the second derivative is negative, that means concave down, which thus means a maximum. The other option is if the second derivative is positive, positive says concave up. If it's concave up, what's in that graph? A minimum. And that's what we're going to talk about as we go through some of these examples here. But that is our second derivative test, how we can use the first and second derivative together to determine a max or a min. And then you're not necessarily having to worry about, okay, what's my first derivative on the left doing? What's my first derivative on the right doing? Is it increasing, decreasing? You can use the second derivative. Again, it all depends on what kind of information you're given. So let's look at example 3. Suppose f is a polynomial function such that the derivative at 3 equals 0 and the second derivative at 3 equals 3. Sketch the graph of f for inputs close to 3 and indicate the property of the function f at x equals 3. Yes. Yep. So if we look at the first derivative at 3 equals 0, when a derivative, the first derivative equals 0, that means that there is a critical point, yes? So a critical point could include a min, max, or possible IP. Now, how do we know which it is? Well, now we look at the second derivative. The second derivative at that value, well, what do we know about this 3 that it equals here? 3 is positive. Since that 3 is positive, that's going to indicate concave up. If a graph is concave up, think parabola facing up, which does mean local what? Local min. That takes you right back here where we know it's a minimum. Now I believe, does it say sketch? Okay. So sketch the graph. It's a sketch, folks. Nothing fancy. Do we know official values? No, we don't know official values. What am I sketching here? A parabola that's opening up because it's concave up, and that has what happened where? Minimum at 3. Now, that minimum could be on the x-axis. It could be below the x-axis. It could be above the x-axis. We don't know any details about that right now. But we know that. And so this point right here at 3 is a minimum. So that's all that, how all that information goes together there. Okay. Example 4 if you're ready. Suppose f is a polynomial function such that f prime of 3 equals 0 again. F double prime of 3 also equals 0. In addition, f prime is positive for all values of x near x equals 3. Sketch the graph of f near x equals 3 and indicate the significance of the point on the graph of f at x equals 3. Okay, I'm going to go through the same details again just to have it down in writing. F prime of 3 equals 0 tells me what is happening here. Yeah, critical value, critical number, critical point, and so there's either a min, a max, or inflection point. Second derivative also equals 0. What's that tell me? Yeah, we're talking inflection point here, since it is the second derivative equals 0. Now, the other information they gave us, the first derivative is positive. And that is near x equals 3, correct? Yeah. So what does that tell me? What is my graph doing if the first derivative is positive? Doesn't tell me concavity, it tells me increasing or decreasing. So if a first derivative is positive near x equals 3, then that means this graph is going to be increasing. Meaning it's going to, and it says, I think it said on both sides, right? It just said near 3. So that's indicating we're increasing on the left, increasing on the right. Does that further support an inflection point? It does. What am I drawing this time? A cubic. And what is above 3, or what is at 3, at the x equals 3 point? That's where your inflection point is, yes? And again, we don't know where this is drawn in relation to up, down, whatever. We don't have that information. But we know that our inflection point is happening at 3. Okay? So inflection point. Okay? Important to be able to decipher all this information. I'll be honest, it takes me a moment to sometimes process it all when I'm first putting it together. So, okay. Example 5, we have to find a little bit more of our information here. This time we're actually given a function, f of x equals x to the 4th. Use the first and second derivative to describe the graph of f near x equals 0. So that means we need to know what's happening at 0 and left and right of 0. Okay, so let's talk first derivative. What is the first derivative of x to the 4th? 4x to the 3rd. Everyone okay with that? Okay. They want to know what is happening. So I'm going to leave a gap here at 0 or around 0. So first of all, what do you know about the derivative at 0? In other words, if I go back and plug 0 in, what am I going to find here? 0 cubed is 0 times 4 is 0. So if the first derivative equals 0, what do I know right now? It's a minimum, max, or inflection point. So it's some type of critical point, yes? Okay. Now, what do we decide? What do we have to look at to decide what's going on around it? Okay, I'm going to look at second derivative in a moment. If I'm just looking at first derivative, though, to determine, how do I determine if this is a min or a max? Or a possible inflection point? Okay, look at points at either side of it. For instance, what are close points close to 0? 1 and -1. So let's look at the derivative at -1 and the derivative at 1. What do you know about the derivative at -1? It's -1/3, so it's a -1 times 4. So it is -4, which most importantly it is negative, which means decreasing. Okay, since it is less than 0. What about when you put in 1 on the right? Yeah, you put in 1, it becomes +4, which the key there is greater than 0 or positive. My first derivative is positive. My graph is increasing. Okay, so what are we suspecting here? Decreasing, critical point, increasing. So we're going to assume, or based on what we know right now, that there's a local minimum. Oops. Now it also asks us to look at the second derivative, yes? So, first derivative was 4x cubed. What's the second derivative?
36x squared.
I'm going to go with 12x squared.
Yeah. 3 multiplied by 12, and then multiplied again by 12.
I say you multiplied by 3 twice is what you did for whatever. I don't know why, but okay. So, what is happening with the second derivative at 0? Plug in 0. It's still 0. Okay. Let's look on either side of it. So, what about the second derivative? Is that a... Okay. For whatever reason, I had just had F single prime written down at this point, which I was just making sure it was just a mistake. Okay, so what happens when we put in -1? You get a positive value. Yes, officially positive 12. Again, all that we care is that it's positive. What about over here when you plug in +1? It's also positive. So what's that telling me? Concave up. Okay. One last one, I think. The graph below represents, and if you can't read that, that is f double prime, the second derivative of f. So right there, it's f double prime. Important to note that. Discuss the basic shape of the graph of f. Thoughts?
Where the graph is increasing, then it would be concave up.
So,
On the spot was by the x-axis.
okay, yeah, I was going to say, I think he used the word increasing, but I don't really want to talk increasing, but these two sections right there, the second derivative is above the x-axis. If the second derivative is above the x-axis, that means the second derivative is positive. What's going on when the second derivative is positive? My graph is concave up. So that means what? When x is left of negative 2, so I'm going to say when x is less than negative 2, our second derivative is greater than 0, which means concave up. And then if I jump down to the bottom, we also just talked about when, the other option was when x is greater than 2. The second derivative is greater than 0, and that's also concave up. Okay. Okay. So just because I'm kind of trying to go in order across the graph, that's why I kind of space these out. So right here at negative 2 and 2, my graph is neither positive nor negative. My graph, the second derivative graph equals 0, yes? And what happens when the graph equals 0? The second derivative equals 0, that is? Yeah. So when x equals negative 2 and when x equals positive 2, the second derivative is 0. And we're going to be talking inflection points here. And really, we know we're going to be talking inflection points because does my concavity change at those points? And it does, because what's happening down here? From negative 2 to positive 2, my second derivative is negative. A negative second derivative means concave down. And so I'm going to say when 2 is less than x is less than 2, that's when my second derivative is less than 0. And so that means it is concave down. Any thoughts of what this graph will look like after you get that done writing down the stuff down? It's concave up, there's an inflection point, it's concave down, inflection point, and then concave up again. Could be a quartic. And would a quartic make sense? Because what does this look like it could be? This looks like it could be a parabola in x to the second, right? And if this is the second derivative, then as you go up, the first derivative would be a cubic, x to the third. My original graph would be an x to the fourth. Which version of a quartic would this look like? If it starts off concave up shaping, inflection point, concave down shaping, inflection point, concave up shaping. Yeah, can you visualize a W here? Think about it with me. And nothing says your W would have to be equal. We don't, again, we're not talking there. But think about it. My graph starts off as concave up, yes? At some point, right there maybe, it changes to concave down. So that would be an example of like where negative 2 might be at. And it's concave down. At some point over here, it changes again to concave up. And so that would be an example of like where 2 could be. Okay? Questions there?